Oh, well deserved. I'm glad you
Yeah, that's nice. I'm not worried about it. I'm really, like, my pocket's half when I'm mostly I'm really excited.
Oh, I think it was. I mean,
filter it, and then we'll start in about just 1 minute. Is it on? Oh, okay. All right, welcome back, everyone. Thank you. I hope you enjoyed lunch. We're now in our afternoon session of the poetically named ISM Beginnings from Stellar Ends. And it's my pleasure to introduce our invited speaker starting this session, which is Makaka Matsura, talking about pars in planetary nebulae. So over to you.
Okay, that's great. So my talk is about JWST spectral mapping of planet nebula NC6302. Maybe planet nebula may be unfamiliar, but you hear the word something like dust, PAHs, and also bubble and disk. So maybe you may see something familiar in some other object in this simple object. So I'm going to start with what is the planet nebula Roma stars stellar evolution. So this is an HR diagram. When the stars leave the main sequence, it's going to red giant phase first and going up to asymptotic giant branch, so-called AGB phase as a second evolution phase on the left side. So when the star is in AGB phase, the stars are slowly pulsating. And when the star pulsates, because gravity of the surface gravity is so low, the gas slowly escapes from the surface of the stars, and the gas forms so-called circumstellar envelope. This circumstellar envelope is filled with gas and dust, but typically because the central star is only about a few thousand Kelvin, the circumstellar gas is typically about 10 to 1,000 Kelvin only. Once these AGB stars stop the nuclear fusion, it's going to evolve into the left side high temperature regime and go into the planetary nebula. So then the central star of the planetary nebula is typically white dwarf, and this white dwarf can emit significant amount of UV. So there's an envelope sometimes formed by AGB stars in the surrounding, and the central star is white dwarf. They emit a lot of UV radiation. So planetary nebula is considered to be typical PDR photodissociation region surrounding the so-called white dwarf, which has about effective temperature of up to 300,000 kelvins. So why we study the planetary nebula? It has a central star is white. Its central star is a white dwarf, and it has this UV radiation. And some of them has so-called disk or torus, which is, you can see in optical, this is the extinction as a dark line across. So this is really, the planet nebula is very ideal case to study so-called UV light, what's happen to the chemistry and dust and the strong UV radiation. It could be the PDR model, but we may need actually XDR model as well. And it has a dusty disk, which can be analog to protoplanet disk. And the largest question in this particular field is which kind of dust has been formed in this type of stars and how much of the dust is ejected at the end of the stellar evolution of Roma stars. So this is the so-called dusty disk, which is quite well known to be, now probably well accepted that they are made from the binary system. So the primary star is losing mass, and the so-called secondary star is orbiting around. So the outflow from the central star is trapped in the momentum of the binary companion and form the so-called binary disk. So this is the edge on view, but I mean it's perpendicular to the actual disk object. So this is the so-called disk. So if you go into the primary and binary, it's formed the nice circumstellar disk. And if you go to, when the stars leave the HB phase, what will happen is this, sorry, I can't find the mark, sorry. So what's happened is, if there's a disk perpendicular to this screen, and white dwarf is slowly lose the mass, and then it's ejected to so-called bubble around. That's what we see in so-called NGC6302, so-called known butterfly nebula. That's what is believed to be happening at the moment. So NG6302, that is our target. The central star's temperature, central star is a white dwarf, and temperature is about 200,000 Kelvin. So one of the hottest central stars of planetary nebula we know so far. And luminosity is about 1400 solar luminosity. So in terms of stellar evolution, it's very top of the white dwarf phase. It has not cooled down yet. It's just top of the luminosity range of white dwarf. It has a disk, or maybe a torus, I should say, because of the thickness. So that's making a dust extinction in optical. So it's really ideal case to see what's going on around the disk, and also, of course, bipolar outflow itself. Another important characteristic of this object is this object is known to be oxygen-rich. There are more oxygen atoms than carbon-rich, but it contains both carbon-rich and oxygen-rich dust in single object. So carbon-rich, what I meant is so-called PAHs, polyaromatic hydrocarbons, and oxygen-rich dust is represented by crystallized silicates. So as a motivation of the JWST observations, we want to test how to form the crystallized silicate. In the dust, there are typically so-called amorphous dust, which has a random direction aligned structure, whereas the crystalline dust is nicely structured dust. There are two different types of dust exist in the interstellar medium. So typically, when we see the amorphous dust, it's maybe believed so-called non-equilibrium chemistry, but it sounds a little bit more complicated. But that is what we can see as the exhaust fume of the so-called diesel engine. So engine of the car make the gas really hot, and then that is come out from the engine suddenly. So in this case, temperature and density drop so sharply when the hot gas ejected the cold meet with the cold gas. In this case, the temperature and density change is much faster than the chemical reaction time. In this case, it believed to form the amorphous because there's not enough time to make a nicely structured dust grains. So amorphous silicate is a typical dust type we can observe in interstellar medium. The opposite is the crystalline. This is actually diamond. We don't see this one in this object, but it has a really nice structured dust grain. It's believed that this kind of dust may be formed. In case of the diamond, it needs high pressure, but in astronomy, it's called equilibrium chemistry. That means temperature and density may be almost constant in substantial time scale. So when the chemistry to form the dust is happening, it's so stable, so there's enough time for the carbon or silicon align nicely to form the so-called crystalline structure. So crystalline silicates has been detected in comets, some of the AGB stars, planetary nebula, protoplanetary disk, and AGNs. The second objective of our JWST observation is, I should go back one. So what we believe is because when AGB stars, most of the AGB stars are spherically outflow is spherically expanding. So in this case, temperature and density drop sharply. In this case, we believe that it's from AGB amorphous, whereas if there's a disk at the center, like this planetary nebula NC6302, this disk can hold the temperature and density for a long time to form the crystalline silicate. So how to form the crystalline silicate has been formed in ISO-SWS, and it has been proposed to form the disk, but we haven't confirmed because ISO-SWS did not have spatial resolution to resolve the disk and outflow, but JWST has a resolution, so that's why we wanted to observe this object. The second motivation to observe this object is why there's two different chemical type of dust existing in one single object. So this object has pHs and crystalline silicate in a single object. So typically in AGB stars, we look at the abundance of carbon and oxygen. And if there's more carbon, we call it carbon rich. And if there's more oxygen than carbon, it's called oxygen rich. If it's carbon rich, you probably see acetylene HCN, and also probably pH may be formed in this condition. I forgot to say one thing. Some of the AGB stars can actually synthesize the carbon. So while the AGB phase, they can turn from oxygen rich to carbon rich. But this object is known to be oxygen rich. So they may not have formed the carbon rich molecule like these ones. Whereas if it's oxygen rich, the molecule you may typically form is maybe water, silicon monoxide, CO2, but also as a crystalline silicates, you can see these magnesium and silicon and oxygen combined together. So the question is how to make two different chemical components dust in a single object. That is a big question. So that is the reason we observe this object. So we requested mini-IFU mapping of this planetary nebula NG6302 at the central region. So it can cover nicely the disk and also part of the bipolar nebula. I mentioned the ISO-SWS. ISO-SWS resolution is actually aperture size is much bigger than this one. So there's no way it can resolve this object spatially. So it has about, this one is about 4.4 tiles, and at the time of cycle 1, it was the largest spectral mapping by MIDI at that time, MIDI-IFU at that time. I think there's a bigger one now. So I start with the first result. It looks a nice image, but actually this is not the image. It's reconstructed from spectral map. So the image is actually a sequence of the ionization potential of different atoms. We have about, including faint ones, about 200 atomic lines detected. So the red one is magnesium, which has ionization potential of about over 200 electrons. And this is a hydrogen combination line. And you can see the high ionization line are much more compact, and going towards a lower ionization potential, it's going to be much extended. So you can see nicely stratification according to the ionization potential, which is expected as a PDR. What we see is exception is iron. Iron 2 line is quite known to be a so-called shock tracer. And shock tracer is actually starting from here. And that one is actually velocity resolved with milli. I hope it works. So this is a milli spectrum mapping. So you can see suddenly iron 2 line kicks out in the bipolar at the 2 bipolar here and here as a jet. So it's clearly resolved. So what's going on in this object is really tricky. So I have to explain a little bit carefully. So in this image, hydrogen recombination line is green, iron 2 is blue, and ALMA 13CO is red. So ALMA 13CO actually traces here, and also there's a big faint one. I don't know if you can see here, but this is actually so-called the torus here, rotating around here. And H1 line is emitted 2 places. So one is actually along the edge of the torus here and here. Another point is, we call it a bubble. It looks like a peanut shape. So what's happened is when bubble is extending and meet with the torus, it's been, because the torus is higher density compared to bubble. So that's why it has a nicely shaped so-called peanuts shape here. So this is an intercept between the bubble and the torus here. The other side is missing because extinction is still high at infrared. And FE jet is starting from outside the bubble. We don't know exactly, but we believe it's like in a balloon, and then put the needle into the balloon and suddenly lost the pressure, so it's just expanding quickly. But physically, I think this is not correct. I think the temperature is not correct. So we don't know exactly, we need to explain, but that we are probably guessing. So if you go back to the previous one, you can see at the intercept, every single emission is found from high ionization potential to molecular hydrogen. Now moving on towards H1, or hydrogen recombination line, which stresses H+ ionized hydrogen, molecular hydrogen, and PAHs. So in the first image, hydrogen is blue, pH is green, and molecular hydrogen is red. So you can see here at the edge of the bubble, it's like a pinkish color because hydrogen, atomic hydrogen and molecular hydrogen overlay. So that's why it looks like this. And pH is slightly offsetting towards our side. And this is instead of a molecular hydrogen, it's put the 13CO to see where the torus is. And this image is enlarged here. And you can see the torus, CO is running here. This is the far side of the torus. And you can see this, the edge of the torus we see in the H1, and the PAH is on the both sides of the torus. So there's the torus and there's the thickness of torus. So the center is cold. I think I have a figure, sorry. So it's not really easy, but we are seeing this torus towards this way, and the CO is the coldest, so it's located in the center, and the pH is H1. We don't know, we are not quite sure this is the really right stratification order, but is pH and H1 is running to both sides of the torus because the radiation, UV radiation hit this disk, and because it's not a flat disk, but it's slightly flared, so that's why we can see the surface of this both region is emitting a H1 and the PAHs. Whenever we observe the planet nebula, we have a little bit problem to understand what's going on. So if you have an idea, it will be great. So we have that the one problem is stratification between H1, molecular hydrogen, and pH is not the same as typical PDR or ion nebula. So I hope you can see it. But if you look at carefully, here is a CO. And there's H1 and H2 are almost corresponding, and the pH is actually outside. It's also here as well. There's H1, H2 are almost corresponding, but pH is found slightly outside. That's not the case in Orion Nebula. For example, this is a Passion alpha image. This is a molecular hydrogen image, and pH is actually, this is the slice of these two images, and the pH is red, and blue one is hydrogen combination line. Peak of the pH is actually almost the same as a peak of the H1. So we don't know why. We don't know exactly yet. But there's a difference in the stratification between so-called typical PDR Orion Nebula against Planet Nebula. One thing we can tell is not because of destruction of pHs, simply because destroying molecular hydrogen is actually easier than destroying pHs. So it's definitely not the destruction. So either that is the effect of the forming of pHs or is an excitation of this particular object. So if it's like a formation, maybe there's a bubble expanding, and also there's a PDR hitting, and the pH is formed on site after destroying the CO. And then that is the reason, because the chemical time scale to form pH is a little bit longer than forming the molecular hydrogen. So we may be able to see some maybe pH behind the molecular hydrogen. But that's a speculation. So if you have alternative idea, I'm really happy to discuss. And we have detected CH3+. That is considered to be one of the carbon-rich molecules which may be involved in the formation of PAHs. Resolution is not really great, sorry. So in this image, pink one is CH3+, and the blue one is PAHs. And I hope you can see, but CH3+ is actually sitting just inside of PAHs and almost corresponds to molecular hydrogen. And if you compare the ALMA CO, it's even more amazing. You can see CH+, you can see there's an intercept here, and you can see the bubble is spreading across towards this way. And then you can see there's a CH+, and CO is actually slightly outside of the CH3+. So if you believe that is evidence of the CO is destroyed and start forming carbon chemistry, that's one way the interpretation, but we are not quite sure about that point yet. Now move on to the crystalline silicate and dusty torus. So this is a mini image. How much time do I have left? 5, okay. So this is a mini image. And you can see there's a still dark line here. That is the extinction of the torus, even at mid-infrared. So this is an image taken by hydrogen recombination lines, but different wavelengths. So this is an ALMA image taken at 1300 micron. And this is a 5 milli image, and if you go to the HST images, you can see this part is getting bigger and bigger because extinction in optical is getting larger. So it's completely obscured in optical and near infrared. But using these properties, this one is transparent into the against the dust, you can estimate the dust extinction and this torus as a foreground. If it's like a flat single straight line, ignoring scattering, Carl may be smiling, then you can get extinction about nearly 2.8 magnitude at 5 micron. So even at mid-infrared, it's about nearly 3 magnitude of extinction at this disk. So we measure the extinction curve. This is the first slide of spectra of this project. But anyway, so this is the extinction to the torus we measured. So this thick blue one is the measured spectra all the way down there. So this dust line is typical ISM dust that has come from the Weinberger and the drains, and RV equals 3. in this case, typical ISM extinction has a really sharp silicate feature, but we don't really see this one. But this silicate feature is much broader and also much broader. And to fit this one, I mean, this particular calculation is actually 2 micron size of amorphous silicates. So it seems like this disk actually contains a large amount of large dust grains rather than typical ISM grain distribution, which contains a lot of small and large dust grains. On top of that, you can see small features there. We don't know this one yet, although we believe foster line, but not quite sure. All of these small features, and these are all crystalline silicates. We try to fit these ones, not perfect yet, but we believe most of these features are explained by forsterite and quartz. And some of them may be enstatite, but I'm not quite sure about that one. So in this disk, approximately 95% of the dust is amorphous and 5% of the dust is crystalline formation. So there was a hypothesis time from the ISO era that the crystalline silicates are formed in the disk and tori when there's a stable disk. And indeed, majority of crystalline silicates are actually found in the torus. But we do detect the crystalline silicate itself, not only the torus, but also the bipolar as well. So I would say maybe detecting large dust grains, the planetary nebulous torus may be so-called analog of the protoplanetary disk. Okay, here's a summary of my talk. Thank you for your attention.
Thank you so much. We have time for several questions. So who has a question?
I forgot, I couldn't include, but this is the actual specs of integrated one. So you can see so many lines. Most of these ones are strong ones, but including faint ones, there are nearly 200 atomic lines. So it's enormously time consuming to work on this data.
I'm wondering about the PA versus H2 question and the geometry. Could it be that we're seeing the outer edge of the disk? So the pods would be outside or the torus, so the pods would be outside of the H2 in that.
Even here.
That would look like outside. Yeah, exactly.
Yeah, that is one thing, but then we have this side again, the same stratification again.
Okay,
so
sorry.
I think we probably believe that this stratification is for the same way. We believe, yeah.
Yeah.
I mean, it can be different, but we believe that both are same stratification.
Liz?
Thank you so much for that talk. I'm wondering how much you think the in situ ISM could be contaminating some of what you're observing here, specifically the pHs, since it wasn't oxygen rich.
Okay, pH is a bit hard to tell, but because it's so close to the bipolar center, we believe the majority of them are coming from the planetary nebula. Obviously, the dust itself, silicate is easier to estimate the mass, so we can tell that must come from AGB stars because it's very localized. Obviously, for the pHs, we did subtract the ISM on the nearby blank stars, blank regions. So we believe there's no pHs. If you look at the image, there's some blank sky there and there. So I think probably most of them are probably from the object itself.
Use chair's privilege for one quick last question, which is, it's very nice to be seeing paths like forming in situ in the act here.
That hypothesis, don't believe what I say.
I believe you that the wind is clearly localized. Are you able to compare these environmental conditions to analogous environments, like in PDRs? Like, can you say if they're forming here, they should be forming in these parts of PDRs?
Oh, that's, well, we like to, but there are a lot of steps we have to do it. So obviously, we have to understand local condition, including the electron temperature, electron density, to get the gas density, gas temperature, etc., to form the PAHs. Another thing is why there's a bubble there. That's another question, because if you follow the so-called planet nebula, they have a smaller continuous ejection of the bipolar. It's not supposed to be a bubble. To form the bubble, you have to have an infall of binary companion to the primary, to the white dwarf, and eject suddenly with triggering the X-ray radiation to have the bubble. So if it's like a single stellar evolution, we are not supposed to see the bubble, so we can't explain. So there are so many physical and astronomical questions to answer before we can apply what we have learned from this object to general knowledge. But one thing I can tell is UV is extremely strong. I can't remember the exact number, but it's much stronger than Orion Nebula. That I can tell.
Oh, thank you very much again. Next speaker.
Stephen, you So forward and backwards, pointing that. If that doesn't work, you can use the laser pointer. And the time over there.
Okay. Our next speaker is Charlotte Smith-Perez, who is carrying on our journey into paths in hydrodynamical. So thank you for that. Over to you.
Thank you. Well, first of all, I'd like to thank the conference organizers for organizing this great conference. And well, hello everyone, and welcome to my talk. I'm Charlotte Smith-Perez, and I'll be presenting to you today for the first time as a master's student from Western University about characterizing the polycyclic aromatic hydrocarbon emission in the planetary nebula NGC 7027 using JWST spectral data. Okay, so if there's one thing I'd like to convey in my presentation today, it's that the processing of the PAH population across NGC 7027 is revealed by changes in the PAH profile classes. In other words, we see drastic spectral profile changes in the PAH features across the nebula, which indicate different evolutionary stages of the PAH populations. Secondly, that these results are made possible by high-resolution data that we get from JWST. Okay, so what's the context of the project? Well, complex hydrocarbons and PAHs form in the outflows of evolved dying carbon-rich stars. These species are subsequently subjected to chemical processing due to the changing physical and chemical conditions in the outflows. These process species eventually become part of the interstellar medium and subsequent star and planet formation sites. So the goal is to understand how pristine complex hydrocarbons and PAHs in circumstellar environments transition to PAHs in the interstellar medium. Okay, so the target, as I said, is NGC 7027, also known as the Jewel Bug Nebula, and it's a young, hot planetary nebula about 900 parsecs away. It's carbon-rich, which makes it ideal for studying the formation and early evolution of carbonaceous molecules. The observations are spectral cubes from JWST MIRI MRS, and it was originally a calibration target. The data that we use covers a wavelength range of 5 to 18 microns, because this is where we see the mid-infrared PAH emission in the MIRI range. And we can see on the right, this is a HST image of NGC 7027, and I've overlaid the 3-channel frame of views. and the channel that I'll use throughout the presentation is channel 1, which is shown in red, because that's the channel that contains all of the wavelength information that we have. It's important to note as well that the ring that peaks here peaks just inside of where the PA emission peaks. So the PA emission has the same morphology as that elliptical ring, but just outside of that. Okay, so we see strong PA emission in NGC 7027, and that can be seen by the black spectra here. And I've also traced out a continuum like gray. Maybe that's hard to see, but we also have highlighted the main PA emission features in the different colors. So I'll start with the blue, which is the 6.2 feature. That's a carbon-carbon stretching mode and is attributed to ionized PA molecules. Next are the 7.7 and 8.6 features, which are also from carbon-carbon stretching and CH in-plane bending combination modes, and are also attributed to ionized PA molecules. Next, in pink, is the 11.2 feature. That's CH out-of-plane bending mode and is attributed to solo CH bonds. It traces neutral PA molecules. And finally, in yellow, we have the 12.0 and 12.7 micron features, which are also CH out-of-plane bending modes, but due to duo and duo-trio CH bonds. So on the right and the bottom, you can see an example of a PA molecule. And I've shown the edge structure here. So the red point shows a solo CH bond. So that would be the reason that we get the 11.2. And then the duo and trio are shown in the blue and the green. Okay, to get a better picture of the different components within NGC 7027, I'll present the morphology in a 3-color image on the right. So first, in blue, we have the ionized gas. This is a H1 recombination line, and it takes on the form of a bright, clumpy elliptical ring. Then the PA emission, which is shown in red, takes on the form of a bright, clumpy elliptical ring, but just outside of the ionized gas. And finally, in green, is the H2 emission, which is in 2 bright intersecting rings enclosing the ionized region. And on the right, you can sort of see a bigger picture of that. Okay, so the first thing that we note is that the PA ionization fraction varies only slightly. So the 7.7 over 11.2 and the 6.2 over 11.2 are commonly used tracers for the PA ionization fraction. So on this correlation plot, we have ISO and Spitzer integrated spectra from other planetary nebula, and the blue points show the MIRI data. Hopefully everybody can see them because they're all clumped in the bottom here, and I'll talk more about why that is. So we see that the slope traced out by this other planetary nebula data follows the distribution of the blue points, which means that NGC 7027 behaves similarly to other planetary nebulae. However, because all of the points are clumped in the bottom there over a very small range, we conclude that the PA ionization fraction throughout NGC 7027 does not vary much. So typically in photodissociation regions, we see a range of about 2 to 3, and here we see a range of a bit less than 2. So this means that there's not much change in PA charge as you go across the nebula. On the other hand, we see variations in the spectral profiles. So I'll start by introducing the PA classes. So different PA features have been categorized into different classes, and today I'll be talking about Class A and Class B. So Class A, which is shown in orange, is found in the interstellar medium, and it's typical of more processed PA species. Whereas Class B is found in the circumstellar medium, and is typical of unrefined PA molecules. So we see that they have the NGC 7027 has a mix of classes depending on the feature we're looking at. So if we start by looking at the 6.2, the black spectrum of NGC 7027 matches that of Class A. That's consistent with what ISO found in the past. Whereas if we look at the 7.7, which is on the bottom, we have an intermediate between Class A and B. So we designate it Class AB, which is different from what ISO found in the past. ISO found a pure Class B spectrum. And then finally in the 11.2, which is on the top right, we have an intermediate class AB, which is consistent with what ISO found. But what happens when we look at different regions across the nebula? Well, we see a lot of variation. So if we start with the 6.2, we can see that the peak position varies significantly. So this map shows the peak position of the 6.2 feature, and we see that outside and inside the elliptical ring, so the more purple pixels, show a class A, whereas in the elliptical ring itself, which is traced by the yellow, shows a class B profile. We also see that the full width half max varies significantly. So we see a narrow profile outside the elliptical ring, which is shown by the purple pixels. And it's very noisy, but pretty much in the ring and with it inside the ring, we see a class B profile, so broader 6.2 features. Okay, why is this important? Essentially, it means that we have distinct PA populations throughout the nebula. So if we look at the 11.2 next, we also see significant variation in the peak position and full width half max. Again, outside the ring, we see class A with a very narrow profile peaking at a bluer wavelength. And then within the ring itself, we have class B, which is peaking at a redder wavelength and a broader profile. And then inside that, we have class AB, which is an intermediate profile. Okay, next we look at the 7 to 9. So here we see very significant changes. First, I'll explain that the 7.7 feature is broken up into two components here, the 7.6 and the 7.8. And depending on which component is more dominant, then you have either a class A or a class B. So in a class A profile, 7.6 is more dominant, and that is typical of more processed PA species. And in a class B profile, you have the 7.6 being weaker than the 7.8. So that's more typical for unrefined PA species. We also see that the peak positions vary significantly as well. So if we look at that in a little bit more detail, on the right here, we have a map of the 7.8 over the 7.6 peak surface brightness. So taking the ratio of these, the yellower pixels show that the 7.8 is stronger, and the bluer pixels show that the 7.6 is stronger. So outside the elliptical ring, again, consistent with our other features, we see a class A, like a very clear class A that is pretty extreme. And then in the orange spectrum, you see a very clear class B, where the 7.8 is much stronger than the 7.6. And then we also see in other regions, like the different variations between those two extremes. So inside the elliptical ring, we have class A and class AB, and surrounding the H2 ring, we have class AB and B. Okay, so why does all of this matter? Well, because what it's showing is distinct PA populations that have been exposed to different levels of chemical processing from early stages just post-formation to the form that they take on when they enter the interstellar medium. And this is the first time that we've seen two classes within a nebula. So we've never before seen like both extremes of two different classes within one source. Okay, moving on from the classes, but we also see unique 12.0 and 12.7 spectral profiles. So we've also never seen these blended 12.0 and 12.7 profiles, at least to my knowledge. And JWST has revealed this interesting blending between the two features. We're not sure where it comes from yet. This requires more investigation. But potentially there's another component that is contributing that could give us more insight into different characteristics of the PA population, or perhaps the source comes from something else. So to conclude, the processing of the PA population across NGC 7027 is revealed by changes in the PA profile classes. This is the first time that we've seen clearly two classes on both extremes within the same source. And in the outer regions, the PA emission is the PA emission that we see in the interstellar medium, whereas the inner regions exhibit PA emission that we see within the circumstellar medium. So we see both types of emission. Essentially, this is interesting because NGC 7027 is therefore an ideal laboratory to study the early evolution from the formation of PA molecules and complex hydrocarbons to their evolution in the form that we see them in the interstellar medium. Thank you for listening to my talk. And please don't ask me what the practical applications of this is.
Any questions other than that one?
Do you see any evidence for fluorine formation? Been seen in a few planetary nebulae?
No. So there was a paper done by Lau et al. On Sophia data. And in here, you can't see it very clearly. Let me go back a bit. Okay. They hypothesized that, they saw indications of PA formation along what are called the so-called outflows, but we pretty much missed that in our data. So they saw formation, in the corners here. So you can refer to that paper for more information about it, but unfortunately we missed that region in the calibration data that there was.
Really nice talk. So that really nice figure you showed of the 11 micron feature where you showed the shift in the peak, right?
Yeah.
It looked to me maybe, mostly like a component of that is sort of getting taken away, right? It's sort of being eaten into it from the right-hand side or the longer wavelength side.
Yeah.
How do you interpret that? Do you think about multiple components in this feature or something?
Yeah, so there has been revealed multiple components of that. For that, I would refer to my colleague Baria at the back. You can speak to her about that because she decomposed that region very thoroughly. And so I haven't done the decomposition of this feature, so I don't know enough. But yes, it is because of multiple components.
Thanks.
Yep. Thank you for the nice talk. This separation into classes of A and Bs for PAWs is kind of new to me, so I apologize if this is a silly question, but do they correspond, why do you separate them into classes? Do they correspond to different physical conditions of the dust, this class A versus a class B?
Yeah.
What more can they tell you?
Yeah, so they sort of represent in general different characteristics and where we find them. In general, we find class A in the ISM. For example, somewhere like Orion is always class A. And that's characteristic of more processed PA molecules. Whereas class B is unrefined PAs that have just been formed and, perhaps have some more side groups or, something like that have been subjected to less chemical processing. No problem.
Last quick question.
Awesome, thank you. Speaking of the processing, it's really cool that you're seeing the two levels in one object. And I'm wondering, the outer ring of this planetary nebula isn't really interacting with the ISM too much, or is it? I guess I would assume that processing would be done through stars. And I'm wondering what is causing the processing in this particular situation.
Yeah, well, we will have to look into that. I mean, there's not there's a group of stars externally sort of processing them. So it will be the central star, which is very hot, but to figure out the exact mechanisms, it requires more investigation.
Could it be a timescale thing?
It could be, yeah.
Kirsten is about to burst. So,
if you're looking for more pre-MRS data, we changed our calibration source to IC418 planetary nebula. So if you want to check out another planetary nebula, it's cycle 3 and cycle 4.
Thank you. I'll take free data any day.
On that uplifting note, thanks, Sgr A.
Yeah, I have to grab it, but I will even. Sorry, this is not embarrassing. Unknown time left. Okay, everyone. We are about to enter our discussion session, but before that, I just wanted to make a couple of announcements. I'm sure you are all wondering about the Orioles baseball game that was planned tonight, especially because we've been talking about a lot of clouds today, a lot of interstellar medium clouds, but these are not the clouds that we wanted. So it looks like the game is going to be rained out, but we have not heard any official word from the Orioles. So unfortunately, we don't really know whether the game's going to be postponed to later this week, postponed to later this summer, if we can get a refund for all of the tickets that you bought. So we're looking into our options, but we basically just are at the mercy of official communication from the Orioles. As of right now, the game is still going on. If the game continues to go on, you are welcome to grab a poncho and check it out. I may do that. I don't know.
Our seats are mostly undercover.
That's true. Yeah, a very important note is our seats are under like a little bit of awning at the top of it.
Our seats are here beneath this awning.
Yeah.
You are now informed.
So that does give a little bit of cover. So we'll just keep you updated. I've been refreshing their weather page literally every 10 minutes to try and give you guys answers, but this is a non-answer to the questions that you guys have been asking. I'm wondering too. Okay, moving on, I just want to flash the Friday afternoon hack day again. We've gotten some awesome ideas in already, so please submit your hack day idea. You can use it through that QR code. We've also put the link on the Slack channel, and there's a link to it on our website. So lots of places where you can submit your hack day ideas here. That will be Friday afternoon. Okay, and now we are going to get into our first discussion of the symposium. So thank you all for writing discussion ideas on the whiteboard and for voting on them. These were the 3 winning discussion ideas: galactic versus extragalactic star formation efficiency tracers. So this will be led by Tim Davis. Thank you so much, Tim Davis. This topic had the most votes, so it will be done in the auditorium, the largest space. Next, we have what properties/parameters would observers like to see measured in simulations. Mordecai will be leading this. Thank you, Mordecai. This will be held in the cafeteria, and you guys can use the whiteboard, the back of the whiteboard, for your notes. And then lastly, in the cafe conference room, we have using 3D dust maps for H2 regions and 3D metallicity maps in gas. This will be led by Catherine Zucker. Thank you, Catherine. So what you all are going to do is split up into those rooms, whatever question you find most interesting, most engaging, and then you are going to chat amongst attendees for 30 minutes, and then we're going to return back to the auditorium at around 3 o'clock, where we're going to report back what was learned in each room, and then we're going to go into a poster session. All right, is that clear to everyone? Seeing some smiley faces. Awesome. Okay, I'll leave this up so people can figure out where they want to go, and I'm looking forward to discussions with you all. Thank you, Ben. I don't know if it was better to have a whole room clap for you.
Yeah, what's done is done.
We can raise up? That we're going
Yeah,
to raise
it probably
up.
helps
We're going to